So there are a couple different problems here, right? Solve. Already isolated, convert to an exponential. Okay. If I was going to convert that to an exponential, remember the process, right? You take the base to that power equals what's inside the logarithm. What is the base? It's e, right? When you see the ln in your mind, you're thinking, okay, there's the e there, right? It is assumed that there is a base of e. So you're going to say e squared equals x. Okay. Now, this is what the book means when they say exponentiate both sides. If I'm starting with ln of x equals 2, what they're saying is, let's make these the exponents of a base, which is the same as the base of the logarithm. So I'm going to say this e to the ln of x equals e squared. That's what they mean by exponentiating. Now, in the same way that ln of e to the x equals x, so does e to the ln of x. They cancel each other out and you get x. X equals e squared, which is the same thing that we got here. The thing is that if you're going to exponentiate both sides, you know, most of the time when you write something in the exponent, you write it a little smaller, right? And the spacing, if you've already written something like this, it's kind of hard to sometimes stick something in there and make it look like these are appropriately an exponent, which I guess means they should be smaller than the bases you just threw in there. I mean, it always looks a little awkward. And it even sounds a little awkward. I usually even say exponentiate. I would say, and then take exponentials of both sides, which even that doesn't really quite represent what you're doing. But the fact is that if you just convert it to an exponential, you've done the same thing. And that's something we've already done a bunch of times anyways. So I would really prefer to let's just convert it to an exponential. Not exactly what you'll see in the book examples. Now, on the second one, this is going to be what we call one-to-one property, Trevor, because you weren't here. But can you imagine how we're going to simplify that one as a first step? Since both sides are log 3s. Exactly. Because it's the same log on both sides, it must be that 5x minus 1 equals x plus 7. It's the one-to-one property, right? Since the logs are the same, the arguments are the same. 5x minus 1 equals x plus 7. And then that's a pretty basic algebra, right? So 4x minus 1 equals 7. 4x equals 8. X equals 2. Okay. How could you check to make sure that that was right? Plug it in, right? Now, it is more important with logarithms to check your answers than it is with exponentials. And the reason is because if you remember, shape of the graph and everything with logarithms, right? A logarithm looks like this. You cannot take the logarithm of a negative number. The graph only starts to the right of the y-axis. So if you had, let's say you plugged this back in and it led to a logarithm of a negative number or the logarithm of 0, which are not in the domain, that would be an extraneous solution. So that's something we have to worry about with logarithms, so we don't. Because what's the domain of an exponential? All real numbers. Right? You can plug anything you want into an exponential, but you can't plug anything you want into a logarithm.